Okay, what I'm realizing is you probably need to know how to use your calculator for this as well. Again, I can only show you how to do it on the TI-84, and not on the other calculators, but I'll show you how to do it on here, and maybe it'll help you do it on your calculator. There's two, so the way we get to this is, if you see up here above vars is DSTR, that's distributions. These are for probability distributions. You need to know how to do this. So you're going to second that. And then you have all these different types of distributions. The one we're looking for here is binomial distribution. You'll notice there's two. Binomial PDF, which stands for just probability distribution function, binomial probability distribution. And then the CDF stands for binomial cumulative distribution function. The difference here is that for the PDF, it's at one value, right? It's at one value of R. So I just want to know what's the probability that two people vote a certain way, or I want to know the probability that I roll exactly a 7, then using this one. The second one is for a range of values. So if I want to know the probability that at least 3 people vote, or I want to know the probability that I get a score, I roll dice and I get a score over 7, then I should be using the cumulative one, right? Also take a note that for the TI-84s, they'll only actually do numbers less than R. So if you want to find the ones that are greater than R, it's easier to find, it's less than or equal to, it's easier to find the probability that's less than or equal to R minus 1, and then subtract that from 1. I'll give you an example of that in just a second so you can see. So let's go back up and do this problem again. We're going to start with problem A, which is what's the probability that exactly 3 members are in favor of the change in conditions. We can do that. That's exactly 3 members, right? So we're going to do the PDF because it's exactly one value. In this case, number of trials is 5. There are 5 members. Our n value is 5. That's also what this meant, right? In this case, the probability of success is 0.72. The x value we're interested in is exactly 3 members. So we're going to put a 3 there, and then we're going to paste this in, and you're going to get 0.293, right? So 29% chance that happens. That's also what you would get if you did this. And if you want me to check that, I can do it at some point and send you a video or something. Whereas here, when we get the what's the probability that at least 3 members, right? So this is asking for part B. It's asking what's the probability that x is at least, that means greater than or equal to 3, right? That's going to be the same as the probability that x is that's the at least. So that's 3 or more. That's going to be the same as the probability of x being less than 3, and then 1 minus that, right? So just notice something real quick. If I just do second distribution, go down, we're doing CDF again because it's a range of values. There's still 5 trials. The probability is still 0.72. In this case, if I put a 3 here, it's going to say less than or equal to 3. All right, so what this is actually going to give us a incorrect answer. So I'm actually thinking we need to put less than or equal to 2 because we don't want it to include 3 in this case, right? We want it to include 2 and below. I want it to be less than or equal to 2 because it includes whatever value this is here. So I actually need to make this 2 and then do it. And you're going to get this, right? And again, this is the probability that it's less than or equal to 2, which I don't want. I want the opposite of that. So I'm going to do 1 minus that, and that'll give me the probability that's greater than or equal to 3, which is 0.86. 862, right? Okay, so let's look at another example. There's a 5% chance that any apple in a crate will have a blemish. We're going to take 25 apples, and we're not going to replace it. Right? Remember, binomial theorem doesn't work if we're not replacing. We want to know what's the probability that exactly 2 of these have blemishes. So we're going to go second, distribute, and we're going to go down to binomial PDF, right? We're doing a single value, so we're doing a one single, or PDF is for single values. The probability is 5%, 0.05. The x value we want to know in this case is 2, right? And then we can just do that. And in this case for A, the probability is 0.231. Right? Now if you want to go to B, what's the probability that at least 1 has a blemish? So what we're asking for is what's the probability that x is greater than or equal to 1. Again, your calculator cannot do x is greater than or equal to 1. So this is the same as, because it's discrete, this is the same as the probability that x is less than 1. Exactly less than 1. Which is actually, no, sorry, this is, yeah, this is the same as the probability x is greater than 0, not including 0, because you can't have, you know, 0.1, 0.2, 0.5. So like these two are actually the same, and then that's going to be the same as the probability 1 minus the probability that x is less than 0, right? Because you can just flip this over, like those two would be the same. Because if you imagine like, you know, if you have a probability here, like this is probability that it's being greater than 1, greater than or equal to 1, and this is the probability here where it's less than 1, then, you know, the total probability has to be these together, right? And so the total probability is 1, so I can find either one. If I know this one, I can find this one by doing 1 minus this one. Hopefully that's not beyond you. So what we're going to do is we're going to do second distribute. We're going to go down to CDF because we want a cumulative. We're still at 25 trials. Probability still 0.05. The x value in this case is going to be 0 because we want to know when is it less than 0, which, you know, it's basically just 0. Which I guess we could do it that other way too. So we can talk about that in a second. But this probability gives us, this piece right here just gives us 0.277. So we're going to do 1 minus that. Oops. 1 minus. Which is 0.723, right? So there's a 72% chance that at least one has a blemish, right? So likely it's one has a blemish. Then we want to know what's the expected number of apples that have a blemish, right? So if I have my 25 apples in here, how many of them do I think are going to have a blemish? Well, for binomial distribution, the expected value, which is the same as the population mean, is just equal to n times p. N is the number of trials, or the number of things, which in this case is 25. Yeah, times the probability, which is 0.05. So we'd say, okay, 25 times 0.05, and that would give us 1.25. So we'd expect about a little over 1 apple every single time we did this. All right, hope this helps.